Hello again, and welcome back to the 12th leg in our marvelous journey through the great cosmos. This one is going to be about dark matter. We are going to look at such fundamental questions as what even is dark matter? We're going to take a look at dark matter in disk galaxies. We're going to take another look at rotation curves and mass decomposition. We're also going to look at dark matter in early type galaxies, and we're going to look at dark matter density profiles in galaxies and galaxy clusters. So a lot of this is basically building on top of things that we already know. But first we need to talk a little bit about what dark matter is, because dark matter hasn't been observed, right? So in that sense, we cannot say what it is. But dark matter is also sometimes used a little bit deceptively when we talk about it, because it is shorthand for a lot of different things, actually. First off, it is shorthand of a set of observations that made us go, what is that? What does that mean? For example, the original observation that the luminous matter in galaxies moves too fast compared to what we would expect if the luminous matter was the only matter there was in galaxies. The rotation curves of disk galaxies, as we have talked about before, and the velocity dispersion in the outer parts of early type galaxies basically show the same dilemma, just not for ordered rotation, because early type galaxies are what they are. It is also the observation that galaxies and gas in galaxy clusters are moving too fast, very, very similar to the way that individual stars inside a galaxy or individual gas clouds inside a galaxy is moving too fast. In the same way, the galaxies and the hot X-ray gas in galaxy clusters also move too fast to be accounted for just by the luminous matter alone. And the X-ray temperatures are too high. Again, if there was only the luminous matter to hold on to it, then there would be a much lower escape velocity, and the particles of the X-ray gas would, on average, be above the escape velocity and would just not be in the clusters anymore. So there's got to be a large mass that holds on to them. There's the observation that gravitational lensing, both weak and strong, is the way it is. Again, there seems to be hidden mass larger than we can account for just by the luminous mass we're looking at. And finally, the CMB measurement on large-scale structure, when we look at the cosmic microwave background, we can see that already at that time, there were these tiny fluctuations in density and temperature. They were fluctuations of 1 part in 100,000. So like the relative fluctuations of, or relative differences in a factor 10 to the minus 5. And those are really actually very small differences. And it turns out that if the universe was made up only of baryons and radiations, then these density fluctuations simply wouldn't have had time to grow, become large and deep enough gravity wells that could have formed galaxies and stars and so on, without there being some kind of pre-existing structure, that like pre-existing gravitational wells that these atoms that the universe consisted of in the very beginning could fall into and help growing right after the epoch of recombination when the CMB was first emitted. So from the CMB, we know that there needed to have been some existing gravity wells that these newly recombined atoms could fall into and help grow faster. Otherwise, there simply wouldn't have been time enough for star and galaxy formation in the universe. Dark matter is also shorthand for a set of hypotheses that we try to use to explain these observations. So it's both the observations and the attempts to explain them. And there are multiple of these hypotheses. One is that dark matter is baryonic, that is simply I don't know, primordial black holes or dark gas or rogue planets or something like that. And it could actually explain the first 3 points here. However, it cannot explain point 4, the CMB, because there wouldn't be that much of that at the time. And also it cannot explain Big Bang nucleosynthesis. It cannot explain the primordial relative abundances of hydrogen, helium, and lithium in the universe. There's also alternative theories of gravity, for example, Mond, but Mond is not, Mond was really like the old and the one that started it, but there's not a lot of people that work with pure Mond anymore. But theory is still also used like as a shorthand for a family of theories of modified gravity. And modified gravity can model all of the observations that we showed above fairly well, but generally not at the same time. Most of the models still require some kind of dark matter particle to exist at the same time as the modified gravity field. And also they kind of sort of end up having the same problem of postulating the existence of things that particle dark matter has. So maybe, but they're not like a dead ringer for like an obvious answer. Then there's what we call hot dark matter, like particle hot dark matter. That would, for example, be neutrinos. That would be very low mass particles with relativistic velocities. They cannot explain all of the observations above, and they give rise to what we call free streaming, where intuitively you can say that these particles simply move too fast to be trapped in gravitational wells. So there won't be any gravitational collapse and eventual star formation and galaxy formation with hot dark matter. It simply moves too fast. It doesn't care about gravity wells until they become way, way too large. Then there's cold dark matter, which is like more massive, slower particles. And cold dark matter can explain all of these observations, and they are slow enough to form the structures we observe. And cold dark matter is also the one hypothesis that best explains the CMB observations. There's also what we call warm dark matter, which is also pretty good at explaining all these things. And maybe it could be a combination of cold and warm dark matter. We don't know. But these also explains all these observations fairly well. However, cold and warm particle dark matter have one big problem in common. We haven't detected them. We haven't found them anywhere. Like, they're still just the postulate. And on top of that, they're pretty hard to reconcile with the standard model of particle physics. So that's another problem. So what is dark matter? It could be a kind of particle. Most of us believe it is, but it is not a settled question. But dark matter is also simply a set of observations about the universe, and it is also a set of theories or set of hypotheses, set of attempts to account for these observations. To take a look at dark matter from rotation curves in disk galaxies, I have here made, I think, the only flowchart in the entire course, and I apologize profoundly. I promise to never do it again. But this shows, like, step by step how we can estimate the dark matter fraction, if any, in a galaxy, in a rotating disk galaxy. So first, basically what we need to find, if we look at the bottom first, we need to find the visible mass profile, and we need to measure the observed velocity profile. So we need to find the visible mass profile, and from the visible mass profile, we can calculate a rotation velocity profile, right? We can say from the visible mass at radius r, we have inside radius r, we have a mass that is so and so much. that should give us a rotation velocity, a circular velocity of so and so much. Then we can go and compare that velocity profile with the actual observed velocity profile. And if we see a discrepancy between these two velocity profiles, that means that there must be dark matter. Well, this only works, of course, if we have accounted for all the baryonic matter that we have. So the way we do that is that we measure the surface brightness profile of stellar light. We get the mass profile either from what is called the maximum disk model or from population synthesis modeling. We get the mass to light ratio, and then from the light and our model of the mass to light ratio, we get the total stellar mass. On top of that, we also get the gas mass profile. We add up the 21 centimeter flux and use that the mass of neutral hydrogen is proportional to the luminosity of 21 centimeter emission. And from those together, we get the total baryonic visible mass there. And then we can measure the actual observed velocity profile of the galaxy. And again, we compare those two. And if there is a difference between the two, then that must be dark matter, because we have ruled out any other contribution at this point. Here we have an example of some mass and velocity profiles of various galaxies. So what we have here is an SA galaxy, an SC galaxy, and a dwarf irregular. And what we see here is that there is a gas disk, there's a stellar disk, and there's a bulge. The gas disk is the short dashes, the stellar disk is the long dashes, and the bulge is the dots. And we can see that even if we look at NGC 5533, we can see that in the inner parts, those account pretty well for the rotation profile of the galaxy. But we don't need to get very far out before even the sum of these masses simply cannot account for the measured rotation velocity anymore. And that means that we get this fully drawn curve here showing us that a larger and larger contribution to the mass density out here must come from dark matter, because it cannot come from any of the other three main contributors. What we see here in the bottom is the mass inside, like the accumulated mass inside of a given radius. We can see that in the inner part, the baryons are dominating, but it doesn't get very far out before they aren't anymore. At that point, the baryon contribution, the accumulated baryon contribution more or less stalls and doesn't really get much larger. But in order to maintain the rotational velocity that we observe, there needs to be a constant addition of mass, like of total mass. And that discrepancy between the total mass and the baryon mass is the dark matter as we see it up here. We see something similar in SC galaxy. We also see that it is less steep in the center, but we also see basically a very similar profile, except there isn't really a bulge in this galaxy. But then we see that in this dwarf irregular galaxy, actually the stellar disk and the gas disk together accounts pretty nicely for the rotational curve that we observe. So in this galaxy, actually, there basically is no dark matter halo. This is a rare occurrence, but it happens. And also it goes to show that the mass, like the baryonic to dark matter fraction in galaxies, can vary a lot, because this one has a very low dark matter fraction in it. And now we're going to take a look at where the dark matter is that we see. Again, we're going back to the total mass and mass light ratios for disk galaxies. And we see, right, that all of these various galaxies, all these rotation curves, they go up and then they settle at a constant value, as we have talked about multiple times before in this course. If we only had the visible mass to pull on these stars, we would see that the velocity, the circular velocity, would go down pretty quickly and go further and further down as we went further and further out. This simply doesn't happen. It stays the same. This means that there has to be a very large amount of mass. There has to be an almost unchanged mass density of total mass very, very far out in these galaxies, out to very large radii. And that means that we get that, they're constant out to like, until we basically cannot measure the stars anymore because they become too faint. We find that the typical total mass and mass-to-light ratios are lower bounds, right? Because we can only measure out to a certain point. That means that, and because we have all the visible mass concentrated in the center and we can only measure the mass out here, we cannot measure all the dark matter that might be outside of this radius. So the mass-to-light ratio that we measure is actually, again, a lower bound for the actual dark matter mass. But we still, when we try to account for this, we typically find that the mass-to-light ratio is between 5 and 25 for a disk galaxy. From cosmology, we know that the omega matter, like the matter density parameter in the universe, is very close to the critical matter density parameter, which is the one where the universe is exactly flat. But dark matter in disk galaxies is far below the critical density, the critical omega matter. It's similar to that of baryonic matter. It's it's a few times higher, but not by a whole lot. It's definitely multiple times too low to account for it. So we need to look for the missing dark matter outside of disk galaxies. One place it can be, of course, is in early type galaxies. And in early type galaxies, we can estimate the dark matter fraction in a way that is very similar to the way we do it in disk galaxies, except again, we need to take into account the unordered motion of the unordered orbits of stars in early type galaxies. So we have to use velocity dispersions rather than rotational velocities and so on. From this, we can use the dynamical mass. We can estimate the dynamical mass by, for example, velocity dispersions and so on. We can find the luminous mass from photometry of stars and gas. Again, we need to have some kind of handle on the mass-to-light ratio of the stars so that we can use the stellar light to infer the mass. But it is not super important because we know, right, that the hot X-ray gas makes up the majority of this mass, typically at least. And that we can measure more easily because it is optically thin and we know its properties better than we know the properties of the stellar population. And so from that, we can measure the visible mass of the X-ray gas in the stars and we can measure the dynamical mass, and the dark matter mass is simply the difference between these, just as it was in disk galaxies. Again, the dynamical mass can be estimated using either, for example, the virial theorem or dynamical modeling, as we talked about before, or from weak gravitational lensing, as we have also talked about before, for example, with the bullet cluster. And very occasionally, we also have small amounts of residual H1 in early type galaxies, which can be used to construct rotation curves. But that is not the way it usually works. But it can happen. And from all these measurements, we have gotten at this point that the total mass-to-light ratio for elliptical galaxies is around 50. So it's between a factor of 2 to a factor of 10 higher than the mass-to-light ratio in typical star-forming galaxies, measured out to around 50 kiloparsecs. But it's still not quite enough to account for the amount of dark matter that we know from cosmology there has to be. Dark matter density profiles is something we have looked at before, right? We didn't talk so much about specifically dark matter density profiles, but they were density profiles. We know that these density profiles can have various mathematical formulations. We can have a power law. We can have an isothermal sphere. We can have a chord pseudo-isothermal profile. And we can have the NFW profile. We see all these different profiles plotted here together with a typical stellar disk and a typical, or not a typical, this is for a specific galaxy, but the stellar disk and an actual rotation curve as measured. We can also see that sometimes it's a little bit difficult to tell exactly which one of these profiles is the most correct, right? It looks like all these profiles actually fit quite well with the observed data. The pseudo-isothermal is maybe not that good, but the power law and the NFW fit look almost equally good. There's also the so-called Inasto profile, which we see in the course book, which is mathematically equivalent to the Sursich profile, but it's given in 3D rather than projected 2D coordinates. And as I said, uncertainties and degeneracies can make it hard to find the exact distribution of dark matter from the kinematics, but different functional forms of the dark matter profile can be consistent with the same data. But it seems that the NFW profile seems to occur, you can say naturally, there's of course not, but it seems to emerge without being pre-programmed in numerical simulations, which is a sign that might be something that emerges from the fundamental laws of physics. However, we also have this thing called the cusp core problem, which tells us that in simulations in dark matter profiles, pretty much all the dark matter profiles that fit the data and that occur in simulations all have a cusp, basically meaning that their matter density, their mass density diverge in the center of the galaxy. They tend towards infinity in the very center of the galaxy. And that is simply not what we observe. But all these profiles seem to describe the data very well once we get outside of the very central parts of or regions of such a galaxy. So that's what is called the cusp core problem, that these density profile tells us that there should be a cusp in these galaxies, but typically there isn't. In the center, they all seem like they have a core or just a normal power law profile. But this can be accounted for by the fact that there is actually quite a lot of baryonic matter in the very central parts of these galaxies. Remember that the majority of the dark matter is often found at larger radii than the baryonic matter, which is more clustered around the very central regions of a galaxy. And that means that there can be enough baryonic matter in there that it can actually start to dictate how the dark matter profile behaves rather than the other way around, which could be a good explanation as to why we see profiles that want to have a cusp in the center, but actually do have a core. So this has been considered one of the main problems of dark matter theories in the past. But as we have gotten further and thinking about it, it does not seem like it is actually such a big challenge to particle dark matter after all. That was it for this lecture number 12. This was a rather short one with only one part. Here are the discussion questions that I hope we can think a little bit about until we meet. The first one says, question A, rotation curves are used to measure the amount of dark matter in spiral galaxies. How does the DM content and distribution vary with galaxy type? Why does the rotation curve have different shapes in different types of galaxy? For example, rising more slowly. And question B, suppose you want to measure the dark matter fraction and profiles of galaxies in the early universe at high redshift. What type of instruments and methods would be good to use? Discuss what makes it difficult to perform this kind of studies at high redshift. That's it. Thank you for sticking with me this far, and I will be looking forward to seeing you in the next one. Bye for now.